Okay, what I'm going to do is going to cover some basic properties of Fourier transforms. And then we'll give it up for today, okay? Firstly, Fourier transforms, you can talk about linearity of Fourier transforms, okay? If f of t and g of t are functions with transforms big F omega and big G omega respectively, then if you add them together, then the Fourier transform of their sum is the sum of the two Fourier transforms. That's called linearity. And if k is any constant, if you multiply a function by k, then the Fourier transform of that is the Fourier transform multiplied by k. Okay, that means it's linear. So, as an example, we've got this. Here is our time domain function. Okay, it's in terms of time. We've got t here, and we multiply. They're both decaying exponentials added together. Okay, heaviside step function there. Ut just means that anything less than 0 we ignore. We've done the Fourier transform of e to the minus alpha t. Okay, if you remember. It's right on the screen. If you remember e to the minus alpha t. Oh dear. This is not calibrated whatsoever. It's going to be quite tough to write. Okay, 1 divided by alpha. Okay, was 1 divided by alpha plus j omega. And so here we've got alpha being 1, and here we've got alpha being 2. Okay, and then multiplied by 2, so that's the constant k, okay? So the Fourier transform of that plus the Fourier transform of that, because that's what linearity said. If you've got a sum, you can take the Fourier transform of each individually and add them up. So that's that bit there. And obviously the 2, that's a constant, that can come out, and that can come out. So you get this. And notice that this is e to the minus 1t, ut. And remember that was the case when you've got 1 on the bottom, you get there. That's obviously multiplied by 2, which you get 2 over 1 plus j omega. And then here we've got minus 2. So alpha is 2. So we've got 2 plus j omega, alpha plus j omega, multiplied by 3. So you end up with that as your solution. Okay, so that's just showing you linearity. When you get something that looks quite complicated, it's actually the sum of those two. You can take the Fourier transform of each individually and add them up. Okay, and when you've got a constant, you can just take the constant out. You don't need to worry too much about it. Right, there's this thing called shift properties, okay? And they're called shift properties because you're shifting stuff around along the x-axis, depending on whether that's time or whether that's frequency, okay? And there's two shift properties. There's the time shift property. So f of a function in time that's been shifted by time t0 is equal to the Fourier transform of that multiplied by e to the minus j omega t0. Okay, so the example of that would be a let's have another go at this. So that's f of t, and this is t. Okay, if I shift that rectangle across, so here's f of t, and here's my rectangle. So the width is the same, but I've moved it by a distance here. Okay, so the Fourier transform of this we know, big F omega. If this is minus a, and this is a, we have sync. What do we have? Two a sync omega a. Okay. But here I've shifted this off. If this point here is a t naught minus a, and this point here is t naught plus a, then the width is the same. Okay. So the Fourier transform of the rectangle, you have 2a sinc omega a, but then that's multiplied by e to the minus j omega t naught. Okay, so the Fourier transform of this bit is the same thing, but you multiply it by e to the minus j omega t naught, whatever t naught ends up being. Okay, so that's the same. So it's the same function, but it's shifted across in the time domain. So if you have something in the frequency domain that's shifted across by omega naught, then the time domain signal, the frequency of the time domain signal multiplied by that e to the j omega naught t will give you that frequency shift. So shifting a function in one domain corresponds to a multiplication by a complex exponential function in the other domain. So if you took the inverse Fourier transform of f omega minus omega naught, you'd get e to the j omega naught t times by f of t. There's an example I'm going to show you which will help explain what that means. So here's a g of t, okay, it's a rectangular function between 3 and 5, which looks like that, okay. So you can see this is a rectangular function, width 2, that's been shifted from this point over by a distance of 4, okay. If it was here where where t is 0, you can see that that 0 point is now in the midpoint, which is 4. So t0 is 4. And so we know that for a pulse of width 2, which is what that is, a rectangle pulse, and it's obtained, that's the equation for a pulse of width 2, okay, but it's shifted by 4 units to the right, so we end up with this e to the minus 4 j omega in there times by 2 sinc omega. Okay. So that's shifting in the time domain, and frequency domain is similar. Okay, and there are some exercises at the back that will help you solve those problems as well. Okay. Inversion of the Fourier transform. So like I said, we talked about how to get from from time domain to frequency domain. This is how to go the other direction. Okay, formal inversion looks like that. Okay, so it's very similar, except that we've got the plus there, plus j omega t, and we've got a 1 over 2 pi in front of it. Okay, but you stick in your frequency domain function in here, and you get the time domain function essentially. And as I said, I talked about Laplace transform tables. In reality, we often use a table of standard Fourier transforms to go from one to the other, okay, and backwards and forwards. But here we'll just do a couple of examples where we do it analytically. Standard function, we know it's a sinc, so we know it's a rectangular function, but how does that translate? Well, we know that 2a sinc of omega naught ends up being a rectangular pulse of width 2a, which could be written pa as a function of time. Okay, so it's just a matter of translating that into what we've been given as a frequency domain function. So we've got 20 times sinc 5 omega. Okay, so a is 5. Okay, therefore 2a is 10. So that's what we've got. A is clearly 5, so we've got 10 sinc 5 omega. That equals p5t. Okay, but the thing is we've got 20 sinc, so essentially that's going to be 2 times p5t. Okay, so the inverse Fourier transform of this function is going to be 2 p5t, because we know that 10 sinc 5 omega is p5t, is a pulse of width 10. Okay, a is 5, And obviously 20 is going to be 2 times that, so that's where that comes from. So graphically, there's our function, okay, in the time domain. And we had a sinc function, it's the frequency domain, so sinc function. I'm just going to draw it like that. So there are some more properties of Fourier transforms, okay. Time differentiation property. You've got a function that's a derivative of time. Okay, so you have f of t, you take the first derivative of that with respect to time. Okay. Then that is simply a multiplication by j omega. This is one of the advantages of Fourier transforms. Is differentiations become multiplications. Very nice and easy, okay, by j omega. So you take your f of omega of f of t, and if it's differentiated by time, you just multiply by j omega. Easy peasy. And the duality property, this is important. The Fourier transform of a time domain function gives you the Fourier transform of that, okay, big F omega. But if you take the Fourier transform of big F, which is that function, but with respect to time, you get 2 pi times by the time domain signal, but in terms of a minus omega. Now, it's a bit confusing, but let me show you an example. We've got this pulse of width 2, okay, and we know that this is the solution to that pulse, Fourier transform. If you had the Fourier transform of this term in terms of time, so we've got 2 sinc t. If you took the Fourier transform of that, you get 2 pi times by this in terms of frequency. So and because it's even, p1 minus omega is equal to p1 times by omega. Okay. So what that looks like is here is our function. We take the Fourier transform of it. You get the sinc function. If the time signal was a sinc function, you take the Fourier transform of that. You get back to a rectangle multiplied by 2 pi. Okay. You've got a pulse in terms of time. You take the Fourier transform, you get sinc in terms of omega. If you had a sinc in terms of time, which is what this is, you took the Fourier transform of that, you get back to a rectangle, okay, but multiplied by 2 pi. That's what's called duality. Okay. So informally, the duality property states that we can 2 pi factor interchange the time and frequency domains, provided we put minus omega in the second term. This corresponds to a reflection in the vertical axis. If f of t is even, the function in terms of omega is the same as the function in terms of minus omega, so it doesn't really matter. And that's what's happening there. So if you've got a shape that's a sinc function, but in terms of time, you take the Fourier transform, you get the rectangle, but multiplied by 2 pi.